Next presentation is self-organization of skin organoid with hairprimordia formation in vitro. Dr. Randall B. Witteridge will do this presentation instead of Mingxing Lei. Okay.
I'd like to thank the organizers for inviting me to come and share our data today. And so a number of patients, burn patients, are able now to survive due to improvements in grafting and such, but they aren't able to, they wind up with scars and they're not able to grow hairs or glands, and so their skin winds up being very dry. And also patients with alopecia certainly could benefit from the ability to tissue engineer the formation of skin that can regenerate hairs. And so a number of labs have previously looked at ability to do this using a few different approaches. One was sort of the chamber approach by Dr. Lichty's group. Then there's also the patch assay from Dr. Sten's group. And Lily Lee in our lab had developed a method where she'd associated the epithelium from the mesenchyme and then recombined them at high density onto an integra membrane. And then that enabled her to cut them to form different shapes, as you can see on the right. And then when she implanted them back onto nude mice, she was able to shape the different forms of the hairs that grew, and the hairs wound up having a common orientation. So it was a planar hair forming that she was seeing. And so when Mingxing Lei joined the lab, he was interested in how important self-organization was to the process of morphogenesis. And his approach was threefold. He wanted to look at cell behavior, and for that he did some section and staining and some time-lapse movies to try and image what's going on during the process. Then he wanted to look at molecular mechanisms, which involved transcriptome analysis as well as some functional studies. And then Lily had found that her system worked very well with newborn cells from newborn mice, but it didn't work at all with cells from adult mice. And so he thought that through this in vitro approach, he might be able to restore the ability of the adult cells to regenerate hairs. So our significance is that we hope that it'll contribute to tissue engineering for patients with burns or alopecia. But as I'm about to show you, the morphogenic process is different on an unnatural substrate, like a culture dish, or we use a culture insert, than it would be in vivo. And so we think that a lot of people who are doing organoid cultures may actually start to benefit by looking at what's going on during their development. So what Mingxing did was he separated the epidermis from the dermis, and he trypsinized them each, or trypsinized and collagenazed them each to single-cell suspension, and then mixed them together and placed them on a culture insert for 10 days or 11 days. And what he saw very early was that they formed some aggregates, and then the aggregates grew in size. At day 2, they became a polarized structure that developed a cyst inside at days 3 and 4. And then later on, these cysts fused together or coalesced to form a planar skin that later developed the beginnings of hair formation. And at this point, he would transplant them to the backs of nude mice. And there's a cartoon of the events that's going on down below here. So I want to show you a movie, I guess it's beginning. So this is like 1 second equals 1 hour. At early stages, we have associated cells, and you can see them moving around. And then by 3 to 10 hours, they start to form some aggregates. And the aggregates grow by having individual cells join up, or sometimes you'll see some of the small aggregates are joined together to form larger aggregates. And this continues as the aggregates grow in size. They grow through a similar mechanism at these later times. And then at a certain point, after about 36, 40, 50 hours, whatever, they start to stabilize. And you see that there are fewer cells that are free to move about within the medium. Later on, they start to become polarized. And so they wind up being a skin sphere in the next step once they form cysts. So we get the cyst-like formation that begins to form at about day 2, day 3. And then that's followed by a coalescence where these different spheres will, the cells from the spheres will start to swarm out in a second. You'll see that, and coalesce. And then first it forms a small epidermal plane. and then it forms a larger epidermal plane. And I should mention that these also, there are dermal cells that are also present. We just labeled the epidermal cells, so that's what you're looking at here. And then they form a planarized reconstituted skin. And this just shows some of the cells of the reconstituted skin, and there doesn't seem to be terribly much activity as far as we can see. So then he became interested in what molecular what genes might be turned on that might regulate this process. And so he looked at stages during aggregation and polarization, coalescence, and planarization. And he found a number of genes that were upregulated or downregulated, and examples are shown down below. So at early stages, he sees that PDGF is up during aggregation stage, PRKC is up during the polarization stage, MMP14 is up during coalescence, and CTSL is up during planarization. So we wanted to look at and functionally test these to see what their roles might be. So he had access to small molecule inhibitors to a number of molecules, and just a few of them are shown here. So if he inhibited PDGF using this inhibitor, he found it actually enhanced the formation of aggregates. He used an inhibitor of IGF. He found that it actually blocked it. So this meant that PDGF is normally a negative regulator, whereas IGF is normally a positive regulator. And using this strategy, he found that in addition to IGF, VEGF is also a positive regulator aggregation. Collagen and PKC are positive regulators of polarization, whereas PKR is a negative regulator. Coalescence is helped by WNTs, and MMP14 and EGF inhibits this process, and MMP13 and lamin help to form the planar structure, whereas CTSL and NF-kappa-B inhibit this process. So as I mentioned earlier, the adult cells don't do so well compared to the newborn cells, but the newborn cells do pretty well. So once he's grafted them onto the backs of these mice, you can see that there's nice hair formation. And if you look, you get some nice, there's epidermal formation, there's sebaceous glands, and secondary hair germs, bullous forms nicely. So he was interested in what's going on with the adult cells and why they're not able to form these kind of tissues. And so, whereas the newborn form the nice aggregates early on and then form the polarized and cyst-like structures, the adults will have trouble very early on. So you can see the adults get hung up in the formation of aggregation. So he used a similar strategy to what he did earlier. Here he compared newborn cells to adult cells at different stages during the process. And then he was able to take some of these factors that he identified and add them back, which enabled the adult cells, which normally didn't even begin to form aggregates well and couldn't form regenerative hair follicles. He was able to restore this process by adding these factors back. So first he had to inhibit PKC activity, then he had some growth factors and WNTs, and sequentially MMPs, and then he was able to get the cells to cooperate and form hairs when transplanted to the backs of new mice. And this is for the 2-month-old adult mice. So to summarize, he observed that you get associated cells that then form aggregates, that then form skin cysts, the cysts coalesce and then form a planar hair-bearing skin. He did transcriptome profiling and functional perturbation to show that sequential involvement of IGF, WNTs, extracellular matrix, and MMPs are involved in this process. And then he was able to restore the ability of adult cells to form hair-bearing skin by reactivating some of these morphological transitions that take place in vitro. And so again, the work is done in Dr. Chung's lab, and this is the work of Mingxing Lei, although several other members in the lab also helped, as well as colleagues from China Medical University, Chongqing University, and then we had some mathematical modeling from our friends at the University of Oxford. And the research was funded by the NIAS. So thank you. We'd have to take some questions.
Thank you for your presentation. Do you have any questions? Are you okay? So, we have not enough time. Thank you so much. my presentation. Please move on next presentation.